Hello everyone, I'm sure you're doing awesome. So, we are starting a new series on OS fundamentals because many engineers from top to bottom layer, we do have some kind of gap while understanding what exactly goes behind the OS. For example, when a certain program runs or when a certain request come into a web server, how exactly the OS unfolds everything internally. Understanding those things are very, very essentials for an engineer. And we will in our this video series we will try to take many examples of real world scenarios like the problems that Google is solving or Netflix is solving and how necessary to understand the OS fundamentals are. We will uh, we will actually start realizing that over the time on this. So this is the first part of this series, and what we are going to cover is the basic operating system internals of process execution model. And web server is also some kind of a process. Suppose you are running a Node.js server or .NET Kestrel server. All those things are end of the day is being hosted in operating system, and it handles requests. So those process of handling requests as a web server, how it unfolds, we will explore the whole things in very minute details. Okay, so let's start from the basic, like what is a program and how a given OS deals with it. Suppose you have written a program like the use case, like you are a developer with Google, and you are a developer with the Google Chrome rather. Okay, so what you have written over there is you have written some kind of a program, and from that program you have created Chrome.dll. DLL is basically dynamic link library, and from that you have created something like Chrome.exe. Okay, no, now, when we click on that, what this exe or this package does internally is it goes into your applications, your operating systems frameworks. For example, suppose you have written this code in .NET, it will check whether the .NET is being installed or not. And if it is installed, what it will do is it will run something like .NET Chrome.exe. Okay, and so here one process will be created. Okay, so here one process will be created. So what exactly happens over there is that here you have written a program, like you have written a program, and from that program you basically package it out to, here is the package program known as the executable. And this executable, when you click on it, it starts, and suppose here one process will be created like the P1. Okay, and you start another instance of Chrome, what will happen is again this will run and another process will be created. So when we have two Chrome instances running, that means there are multiple processes are running like P1, P2, and whatnot. If you go to your task manager, you will see that uh, under the Chrome, all these tabs and all other windows, they are being uh, they are being run as different processes. Let's try to represent it pictorially. So suppose there is a user sitting somewhere, and this is the user's machine. What he does is he runs some kind of a program, and behind the scene, whenever he double clicks on that exe, what it does is it runs something like a .NET Chrome.dll. Okay, so instead of exe, we should mark it as a DLL. So ideally, what happens is the executable that we create, this executable, whenever we double click on it, okay, in this executable, whenever we are double clicking, this .NET Chrome.dll will be fired up and this process will be created. So let's write it in a more correct way. So we are double clicking on the application, and we are sending a message to the OS that please load and start this program into the memory. So what OS does is then OS will um, then load this particular process into its memory. Okay, so OS will load the program into memory, We will again go into the detail how this program into the memory is being initialized, and in turn what it does is after this it will create uh, inside its OS container block, it will create a process. Okay, so if you keep on creating like multiple instances of Chrome or multiple tabs, what it will keep on doing is it will be keep on adding, like keep on loading it into the memory, and one new processes will keep on adding up over here. Okay, so now for each of this process, few of the essential parts are there. Okay, for each of this process, few of the essential parts are there. So the first one is of course stack and heap memory allocation. So what goes into stack and what goes into heap, we will take example of the program and we will try to explore that. And then after that there is like state of the process. So for a given timestamp t1, what exactly is the state of the process? We are going to store it somewhere, and both of this thing together will define the runtime behavior of the process. So in runtime, what exactly going on the process? So this is on a very 10,000 feet level. In some processes, this exactly happens. Now let's take this example in terms of this memory and the state and the other details. Okay, so when user sends something into the OS, okay, let's I'm just deleting this one for the time being. What happens is this program will get loaded, right? This program will get loaded, but what it will do is it will be comprising of multiple steps. Like what will happen over here is IL code or the intermediate language code will be generated, and allocation of memory of stack and heap will also happen over here. And for each processes, this thing will keep on repeating, like the IL code generation and the allocation of memory. All of this, all of the processes, although it is starting the same DLL or the same executable, but they will have different memory for their stack and heap, and their IL code will be loaded into memory separately. Okay, so this is one of the important point. Now, as discussed, let's try to understand it via a code. Okay, so let's take this code. I will try to expand it a little bit. So the use case is like you are a developer of booking.com or Airbnb, suppose. Okay, so what Airbnb does is it handles so many number of bookings of user provided, like another user provided roles. So now you need to understand how your traffic is going to being served when you are hosting this particular service of yours, like this service that you have written over here. This particular service of yours you have hosted in your web server. Now some issues are being happening and you need to understand what exactly going behind the scene. Okay, so let's explore this program a little bit to give you some idea. So we are having this main public class, which is a booking service class, which is doing all the booking, but there are some kind of a static elements we have. For example, how much will be the static fee? This will never change, so we keep it as a static. And also the active bookings, how many number of bookings are already being going on, or it is active for a given day, we have put into our cache. This is being active booking. And then whenever like a new booking request come with a user ID and with the nights, what we are going to do is we are just going to create a new object and populate our active bookings dictionary. Okay, so now in whole in our whole architecture of OS, how does this request being put into and how it is being served? Okay, so let's take again in a little bit of diagram approach for our better understanding. So there is a user. What this user is going to do is, because it is a web server of us, it is going to make a post request. Okay, so this post request will come as like slash booking and we are going to pass like user ID equal to 123, some kind of a check-in date. So as you can see here, we are expecting the check-in date, some kind of a check-in date, like it can be 25th 25th June 2025, and also like how many number of nights equal to 3, something like that. One of the user requests that the user is making. Okay, now what will happen is it will at first come to our web server. So the web server can be anything. Suppose a Nginx server that we have, server where we are hosting our application. So just take it as a web server. So web server is another process which is holding our full runtime. Okay, now this has been how it is different from this one. So this is running individually, totally in the in as a standalone application. So this is also running in your operating system, but what it does is it has some other capabilities as well, like it can serve traffics and everything. How it does is, let's see. Okay, so what will happen is in this web server, I will just put it in this way. Our application runtime is running. Okay, application is running, which we call as runtime also. Okay, so whenever we are using this application runtime, or the term like in run, what exactly application invocation, all these things that is being run on the particular hosted web server for a web specific application. So what this web server is going to do is it is going to then pass it on to my application runtime. Okay, so it is going to pass that request to application runtime, and something like there is a invoke command internally in the operating system that happens. So this application runtime for the because we are writing the, we have been displaying the code in C sharp. This is a C sharp code that we wrote. Just think that this application runtime is on .NET right now. Okay, so this is our web server important component, and this is another important component, that is application runtime. Now how application runtime behaves with the memory, that is the most important part, and we are going to take some time to explore that. So this is our memory. Okay, so what exactly is going to happen is when a first request comes, okay, in that request lifecycle, stack frame is allocated. Okay, a stack frame is allocated, and you can think it like, for the time being, for a simplicity purpose, just think it as a thread. Although there are few other thing goes on while we are doing it in the .NET. It is not exactly thread, it is the thread pool is in which serves all this traffic, but let's take it as a thread one. Okay, so what this thread one will do is it will keep on doing multiple things simultaneously. So what is the next thing it will do? Let's write it like this. So this is the first step, and in the second step what it will do is it will read the data segment. Okay, read of data segment. So in the data segment, what it will do is it will see if any static variables and stuff are there or not. So in the data segment, it is going to read the this is, we have declared service fee over here, so this is going to read the service fee. Okay, it's going to read the service fee. Then what it is going to do is it is going to check if any other BSS segments is there or not. There also it will find the uh, it will find our cache. Okay, it will see all the active bookings. Now this whole thing is being done is like a basic stack is being created. Okay, this is a very important understanding, and this is a data segment that is being created. Now I'm going to create another block here. Okay, and we will understand it what exactly happened in a certain program flow. So now the moment a request comes and the stack frame is created, it creates a heap memory for the given booking. Okay, for the given booking object. So the moment we are coming into inside this, this part, you see already we have written a heap memory that is being created. Okay, and what it will do is at the same time the heap will be available for the stack frame to consume. So this stack frame is basically, if I write it, stack frame is program execution flow. Okay, or thread execution flow rather, thread execution flow. So what this stack frame would do is, suppose this is my stack frame, this stack frame can actually access the heap. Okay, and by accessing the heap, what this stack frame can do is this can um, this can get whatever the object is there, and in the program flow it is going to use all of this data segment plus this heap memory, and it will create that given object and update the values accordingly. So what it does is this stack frame, it uses data segment, for example all the stack variables and everything that we have. So now, sorry, static variables and everything that we have. Now static variable and stack is nowhere related here. Stack frame is the basic flow, so that is why we call it a stack trace as well. Whenever a program runs, okay, when we say the stack trace, we will see that in the exact flow in which the particular function or a particular method is being called. That is why we call it a stack trace. Okay, so this stack frame is related to that stack trace. Okay, so once this stack frame comes into the picture, it uses data segment plus what it does is it uses the heap, and it then executes the flow. And once this flow is completed, what happens is at the last stage in the memory, in this memory part, it is going to release the stack frame. And once the stack frame is being released, also operating system at the runtime, what it does is it will clean up the heap memory objects as well. Okay, so then cleanup of heap memory happens. So just try to understand this thing. A web server is getting a request and it is going to invoke a particular application runtime which it is holding. That application runtime will create a stack frame for that program execution flow, which is the exact stack trace that we see in our errors. And that stack frame, what it will do is it will take care of all the data segments, and it will also look into the heap memory. From that heap memory, it will get the data like this booking service. The moment it is hitting here, a heap memory will be created. So stack frame will just start it, and once this memory is created, it will use the data segment and the heap, and the whole flow of this execution like cache active bookings, this will be created, and the booking will be returned, and our flow will be completed. And then it will release the stack frame and it will clean up the heap memory. So that is on very that is the exact flow for a single request. Now what happens at this level once we have released the stack frame? So now again web server will come into play at this time. So after a successful execution, because something is being created, what web server will be noted is created 201. You know about the 200, okay, 201 created, 404 not found, all those HTTP request details, right? So what will happen over here is it will give us this created 201, and this message will be then returned to the user, the endpoint that he has invoked. Okay, so let's try to see it in a more mathematical way. What exactly happened against this whole program that we just saw? Okay, So this is the stack allocation. Let me just put it side by side so we have some little bit better idea. So initially what happens is there is a stack allocation happens, and there is this base price and other details that is being populated over here in the stack frame. Okay, so what exactly is created is there is a booking reference for heap object, for heap address that is being created, and then what we do is we are going to create our heap in this booking object, and you see you can ignore all this part like sync block and the other details. And then one interesting thing happens is the BSS, or the block starting symbol, that is being started at that point of time. So block starting symbol will use this property, okay, of the active booking, which in turn this heap will be interacting with. Okay, and then we are going to have the data segment access, that is the global config. And what this stack frame will do is, this stack frame that we were talking about, this stack frame will take everything into account and execute the program. So all these things step by step is being done by this stack frame only. Okay, by this stack allocation that we are seeing. Okay, now let's level up our problem statement a little bit more. Okay, so let's think how how we are going to address multiple requests at a same time, and how exactly OS helps us in that. Okay, okay, so here suppose two separate requests have come. So what will happen in this case? Like here you saw one key part was that a thread is created, and that thread is actually is kind of a owner of the whole stack frame. So now I need two separate threads or two separate stack frame, whatever the way I am seeing it. So now we have this web server process. Okay, web server process running in my OS, running in my OS. Okay, let's take it here, and then this thread 1 will be there, which is already being created. So in case request 1 comes, okay, so this request 1 comes, this will go to thread 1, and then suppose another request of request 2 comes, it will go to the thread 2. Okay, and what will happen is here this will be like a stack frame will be created, and here also for thread 2 another stack frame will be created. So just think them as like stack frame 1, and this will be like stack frame 2. Okay, and they will have their corresponding separate heap and all the other details, but only thing is that they will update the same cache of they will update the same cache of the dictionary. So ultimately all the process like heap and every other objects whichever will be associated with this, it will be having a separate heap. Okay, but it will have this it will access the same data segment, and what eventually it will do is they will update the same cache, the same cache object, the cache object that we are seeing over here, or the active shared dictionary. So now here only some problem happens whenever we are trying to update a state. Suppose both of these users are coming and they are trying to access the same hotel room for the same time being, then how exactly our system would behave? Those are topic of a different thing, like how we handle locking or mutex or distributed lock, everything comes in play. But please understand these things. If two request comes, two different thread will come in play here. two different stack frame will be created. Those stack frame will have their own heap objects, like the booking objects that will be created here for the request one will be different, and the booking object that will be created here on the stack frame 2 they will be different, and using those heap will be updating our common cache, or like a shared dictionary, I can say. Okay, shared dictionary. To understand the role of kernel in a little bit details, let's introduce that instead of let's introduce database. Okay, so instead of writing into this shared dictionary, so now we are writing our booking details to we are writing booking details to a DB. Okay, to a DB. So now let's see how the request goes along. Okay, and we will see what is the exact role of kernel in this. So here comes the user one. Okay, so from user one request goes, and the request goes into the our server. Okay, so this is again web server. So from this web server, what it does is it from the thread pool. Now this concept of thread pool will be actually interesting. What exactly thread pool is? So all the thread for a given program is available for the thread pool. So it will, from the thread pool, what it will do is it will get a given, it will get a given thread from the thread pool. Okay, and whenever we will be releasing any thread, it will go back to the thread pool. So thread pool is basically like a pool of threads from which we can pick thread as per our will. Okay, so now what we are going to do is this is going to get the thread one. Okay, so after getting this thread one, it is going to request it is going to start our stack frame execution flow. Okay, and this stack frame execution flow will be initiated from our OS. So now here the OS and the stack frame will perform a very important role. So what it is going to do is, now we are as we are going into our database, it is going to make a call to our DB. Okay, so this is what our operating system is going to make a call. Now, interestingly, in this time, because the database is in a different server or in a different place where will be waiting for the query execution, so definitely there will be some kind of a query that will be executed. So what happens is our thread is getting released in this process. Important note, while making a DB call, thread is released. And who take care of this? Kernel keep it back in thread pool. Okay, so kernel make sure that this thread is released, and it will keep it back in the thread pool, and it will keep on listening. Like when I say it means the kernel. It will keep on listening when the DB call is being completed. Okay, so when the DB call is being completed, what will happen is here the thread one will be like, let me write it, thread one released. Okay, so now the query execution is being done, and once the query execution is being completed, okay, it is returning the data, and what will happen is it will again get another thread, and now it will be the responsibility of the OS. So what will happen over here is, now from the thread pool again, it will say get thread 3, suppose. Okay, so it will not be working on thread 1, it will be working on thread 3. So there is no idle time for any thread. No thread is waiting for any given time. What exactly the role of the kernel is? Kernel is in a row is managing all this to and fro of the threads, and whenever we are making a asynchronous call, or we are making some kind of a IO calls, we are waiting for some other systems, okay, to get some data back. Kernel completely frees up the memory and it waits for some kind of a thing called IO CP signal. Okay, so this is basically when this data is completed, what happens is there is something called a IOCP signal that we get. So this IOCP signal, okay, signals the kernel that it needs a thread to proceed. And few interesting things that happen over there is who stores the state of thread 1. So please understand this thing. When thread 1 is being released, I cannot just really let go of the thread, because thread might be having lot of details of that stack frame. So who will be storing that details of those stack frames? Because from there only, when my data comes back, from there only my execution will again start. So I think it is understood that here during this query execution from the thread pool, whenever this stack frame is there, right? So who will be storing this stack frame? So this stack frame is basically from here, it will be basically copied into the thread 3. Okay, and who will be taking care of this? Something called TCB, or thread control block. So thread control block will keep a track of all the given threads which is being waiting for IOCP, or which is being just released. The execution is not being completed, which is just waiting for some kind of a IOCP signal to proceed. So with this case, what will happen is this TCB will take care that now the stack frame is available. Okay, so now we see that stack frame from thread 1 is available with thread 3, and whenever we are getting the kernel is getting the IOCP signal, what it can do is it will tell key take this stack frame, create another thread, and take this execution flow as it is. Now interestingly, here we have touched upon two very important concepts, but two very exclusive contexts as well: PCB and TCB. Okay, so what PCB is? Process control block. So whenever a web server is running, all the memories of that web server, like what is the process ID, what is the stack pointers, what is the different registers that are involved in this web server process, that are being stored into the PCB. So PCB holds important details like process ID, like what is the main process ID, the memory layout, like the text segment code, data segment code, all those details. Like the data segment is definitely goes into the PCB. Okay, so all the memory segment details, and also interestingly, it holds all the details of the TCB. Okay, all the details of the thread control blocks. And what TCB does is, so TCB will hold all the TID, and alongside that it will hold all the registers that it is using, and things like program counter, the stack pointers, and the state. For example, if it is a running, waiting, blocked, the state of a given thread, what exactly is going at that point of time. So basically all the stack, if I have to just sum it up, all the stack frame that we discussed, all the stack frame details it stores. Okay, so that is the basic difference between the PCB and the TCB. And coming back to the discussion of our kernel, so what kernel does is it releases the threads in timely manner and wait for IOCP signal in this flow. Of course, kernel does a lot of other things, but the flow that we are discussing here, it is mostly it mostly does this. And once it receives IOCP, what it does is it will take new thread and ask it to use a given TCB or thread control block. Okay. So now what happens if another request comes at the same time? The moment we discuss this concurrency request, few of the more things will start unraveling for us. Okay, so now our situation is that another request comes, okay, at the same time. So I think by this time you are already started getting a hang of it. What will happen if another request come? Suppose there is another user too, and he makes some kind of a request into the web server at the same time. What it will do is it will just create another thread. Okay, it will just from the thread pool it will go and it will create like get thread 2, and from then onwards what will happen is it will be quite similar to this stack frame allocation TCB, and the stack frame allocation will happen here. And similarly, if it is making any kind of a third party call or a DB call for which the IO waiting is there, it will release that thread, and then it will try to get the thread 4 when the IOCP is being received. Okay. And interestingly, what is the full form of IOCP? It is the input output completion port. So the moment one IO request goes out, if it is waiting for it, it is going to kernel is going to release that thread, and when that IOCP port says that I have got this request back, kernel will again take back the uh, uh, c- t- kernel will again claim one more thread, and it will take the copy of the TCB, it will restore it and execute it. So I think by now it is quite clear. Now we will go into the little details around the compilation and the memory layout uh, of the program flow in a more generic way. So let's take a very simple problem of calculation of addition of two numbers. Okay. So what exactly the developer will do is developer here will create a C# program. Suppose calculate something like calculate.cs, and this calculate.cs, from there he is going to create something like calc.dll. Okay. So now the dynamic library is being created, it is residing on our file system. So in our file system, we do not have any memory right now. What we just have is we have a DLL. Okay, calc.dll, and this DLL, what we are going to do is we are going to run using .NET runtime. How we can run is we can just write .NET calc.dll, and it will be passed to the .NET runtime from here. Okay, it will be passed to .NET runtime from here. Now from .NET runtime, once this is being loaded into the memory, okay, so till this point it was nothing but a simple IL code package. Okay, when I say IL code package, that is intermediate language that is being created. It is a IL code package, and from there what it will do is it will go to the memory, it will go to the memory, and in that memory it is going to allocate PCB and some memories for the our heap and stack and heap, all the other memories will be allocated. Okay, so this is happening on the OS level. So now in the .NET runtime from the file system we are having a simple DLL we are creating on the OS level. The moment we are running this application, we are going to create our memory, allocate process control block and the stack heap, etc. Now let's understand uh, like the thing that we already discussed, what exactly will go to the data segment, what exactly will go to the BSS segment, that is the block starting symbol segment, and what exactly will go to the heap and stack. Okay, BSS segment, there is heap and there is a stack. Why we are doing this exercise? Just to make sure that we understand all these things with a complete details, because for any given programmer or developer this is very very important. So in the data segment what will happen is this static string. Okay, so data segment will got this static string of greeting. Okay, because this is a static and it will be available across all the instances as well. Okay, so in the BSS segment, what we are going to have is uninitialized static variables. So for the time being, we do not have any initialized static variables. So there is basically none here in the BSS segment. Okay, so heap, what it is going to have is, heap is going to hold our calculator object. So the CILC object that is that you see over here, that our heap is going to hold. And what stack is going to do is, so stack is going to do, of course, it will hold x equal to 10, 20, those values, plus it will execute in stack frame the add a comma b. So we are calculating this, right? Add a comma b, and what it will do is, while executing it, stack will access the heap. Okay, stack will access the heap, and it will make sure that it has the correct object from there. So I think now it is pretty clear that from the main thread, we are going to push a stack frame, and in that stack frame, our calculation will keep on happening. So stack frame and stack is kind of not fully synonymous, but stack frame uses this stack of variables in various level. So this is stack or stack frame, we can say, in a interchangeably way. And once those calculation is being done, what stack will do is, it will return to the main thread. Okay, return the data to the data to main thread. Cool. So how heap works, let's take a little bit of more details into. So you remember, I think some time ago we were talking about this runtime, right? So whenever a program is being written, how a runtime will come into picture. Okay, so now uh, the main function of this runtime is creating those objects at the time. So here we have this runtime for us, and what this runtime will do is, this runtime will go to the heap memory and create this calculator object. So here you can see we are doing CALC equal to new calculator. So this new calculator, this object, this will be created into our heap. Okay, so this will be created into our heap, and once this operation is being done, once stack frame has used the heap and stack frame is executed, then like once stack frame is done with the heap, what will happen is, there is something called GC will come in play. Okay, so this is again runtime plus operating system behavior. So this GC, what it will do is it is garbage. It does the garbage collection. So it will just take this heap, and it will go into this heap. It will see that which objects are not being used, and it will just remove or clean up those objects from the heap memory. Okay, so this is like in a very organic or a very simple way, I would say the runtime, heap allocation, and stack memory works together. In this process, one of the very important thing is, what is the relationship between the stack and the heap. So the people who are writing code, it is very essential for them to understand that stack can access heap, but heap doesn't need to access stack. So stack is basically our stack frame, which is holding the program flow. Okay, so we are having, so stack hold the references of the heap object anyway. So how the whole stack reference or the stack frame happens is, it holds the, okay, so this is our stack frame, suppose. Okay, so it holds the reference to the heap, reference of heap, not the direct object. So whenever it needs the object, what it does is, it goes to heap and it takes back the data. it goes to heap and it takes back the data, and what it will keep on doing is it can even write the data to the heap. Suppose a certain property of the objects to be changed, then it can write into the heap that, hey look, I have accessed you and I have made this change. So it can read or write into the heap, but the heap memory cannot access stack. So we got to understand this, that it is only from the stack side. Okay, it is only from the stack side, but heap cannot really, like for example, this flow that I have written, this is not correct. Okay, only from stack the read and write can go into the heap, and whenever a reference object is being required, it will bring it from the heap. The method execution on the stack can dereference it uh, according to its need. Okay, so suppose this calculator method, okay, this sorry, this calc object, okay, this will be leaving onto our heap memory. Now let's talk about how all these concepts actually helps us in our modern computing, because now everything is being abstracted away. All this cloud providers like AWS, Azure, or GCP, they have their own virtual machines in the cloud. So how all these concepts are required in modern computing? Okay, in modern cloud computing rather. So just understand one thing, this EC2 when we are talking about, okay, the elastic computes of AWS that it provides, the virtual machines. So it is essentially a fully fledged OS, be it Linux or Unix or Windows, and understanding the process memory like the stack, heap, and all the other details, it will help you to gauge like how much data, for example, how much data my application might require in the runtime. Okay, so this kind of information, it will help me to right sizing the instance. So sizing the instance is a very important thing. For example, like when you will start working on any kind of cloud infra, you will see that we have to always keep on optimizing our VM size, because these are, although a managed platform, but they are expensive. So if for very simple process I am over provisioning my hardware, then I am wasting my organization's money, as simple as that. And so understanding all these details around the memory and heap and how much memory a certain uh, s- at a certain point of time my application might need is really very important for sizing and understanding what kind of infrastructure I am going to provision. And then there comes like things like ECS and EKS. So that is like Elastic Container Service or the Elastic Kubernetes Services. Here also please understand that the each containerized applications, okay, or the each containers that we see, each containerized app is a process by itself. Okay, so whenever we are having any containerized application that we are hosting in some kind of Kubernetes or some kind of a container host place, so this they themselves are the process, and from the host OS perspective, it is it is nothing but a separate process that keep on running in a same OS. Okay, so that is why the concepts of program, process, program counter, stack, heap, and linking, everything are directly applicable here also. Now comes around one of the king of serverless computing, that is Lambda. So when we are talking about Lambda, uh, so when a Lambda function is invoked, just understand there is something called micro VM that, like, and end of the day, when a Lambda function runs, it nothing but it creates a short-lived VM which is known as a micro VM. Okay, so if we don't understand the memory implications here, that is again going to hit us big time, because the OS concepts are abstracted here in terms of the micro VM, because although AWS manages the process creation and memory allocation, but understanding how much memory my Lambda function might take and the corresponding space complexities and the other details are very essential. So let's take a real world example of Netflix. Okay, so let's take an example like how Netflix leverages OS internals for their encoding process. Okay, so let me talk a little bit about what exactly the encoding process is. Okay, I will just take this line out. Yeah. Okay, so let's talk. Let me take you through in couple of pointers what exactly the encoding process is. So when video is being submitted by your content creation team, okay, then that particular video, so video is in a raw format, okay, it is having a very high resolution, but in reality what we have to cater is we might have to cater users with 240p resolutions also and the users with 8K resolutions also. Okay, so in between many other details will come like the 4K, the 2160p or 1080p, all these things will come in play. Okay, so transcoding or encoding this massive video into various bit rates or formats and streaming them across, it is a own challenge on itself. Now when a particular encoding request comes, okay, suppose there is a content creation team, so they provided this raw video, and what they do is after providing this raw video, one encoding request will come to my system. Okay, suppose I am having a one encoding request comes to my system. So suppose now I am having this EC2 instance of mine. Okay, and what this EC2 instance will do is it will encode all of these things and give me different data like 240p, 720p, 240p, then things like 720p and 1080p. Okay, and whatnot, like it can give me other things as well. So what exactly happens in this case? So there we have our Linux kernel. Okay, just think it in this way. We are having our kernel, and from there our kernel using our C group manager, what it does is for every single process it will allocate a certain amount of memory. Okay, so what it will do is it will enforce, like in terms of our C group manager, it will enforce something like suppose 4 GB memory, okay, and 2 CPU for a given process. Suppose one encoder for 240p job, okay, encoder for 240p job, and this is one thing, this is one process that is getting started, and then suppose the 8K job is also running. Okay, for that probably I am going to need like 16 GB of memory and 6 CPU. So encoder for 1080p 1080p job will run over here. So you understand one very important thing, there is a process isolation we can impose on that using a concept called a very popular concept that is called as CPU pinning. Okay, so what it does is each encoders run as a separate process with a defined memory and a CPU limit via CG groups to ensure fair resource allocation. And this OS scheduler distributes the CPU time also across the encoder process. And this whole concept that you see, like pinning a particular process to given set of CPU core. suppose I am having like a 24 core CPU. So instead of two CPU, I should write a CPU core. That will be more clear to you, I guess. So pinning a particular process to a given set of CPU core is being known as a CPU pinning. And any kind of memory intensive things, like be it this encoding or any other kind of a memory processing things, where we are processing a huge JSON, suppose. In all those cases, this CPU pinning concept is being used, and this is one of the very core application I could come up with for the process execution model that we just discussed. So this C group manager, it can control all these process executions of the time slices and the resource slices. And what it does is this by using encoder, it processes are pinned to specific CPU cores to reduce the context switch and improve the cache locality, and it increases the throughput and efficiency during the compute heavy video encoding task. So we have covered quite a lot of things, guys. Just to sum it up, so we started with the basic internals, like when we are writing a code, what exactly we produce and how exactly OS is going to treat it when we bring it into the memory. Then we went into the internals of our stack and heap memory allocations, and from there we also saw how the stack frame, heap, and everything comes together to execute a certain request that is coming into a web server. And then we jumped into the role of the kernels, like how tactfully kernel handles the thread pools these days, so that none of the threads are idle for a long time. Then we came to the thread control blocks and the PCP, the details like how they come together and helps kernel to manage the states. And then we went to the like kind of a revision to all the things like the data segment, the BSS, how the heap allocation happens, how the stack allocation happens, and how comes stack returns the memory, what is the relationship between the stack and the heap, who can access whom. And then we touched upon few of the cloud components, and then we tried to convert it into a real world concept where the process execution model is actively being used, especially for Netflix, for their very heavy encoding process. So that's the video, guys. I hope things were clear to you. In case you have any doubt or you feel that something needs to be explored more, please comment. Thank you so much. Stay awesome.